Dear student, welcome back. In our last video, we discussing about a chapter called magnetism and matter. In a magnetism and matter, in a last video, I explained about bar magnet. Important thing I consider properties of bar magnet. Not only that, bar magnet has a equivalent solenoid. That important derivations we consider in a last video. Today we'll do the continuation of that chapter. In today's video, we're going to discuss two important things. One is related to magnetic field line. You may heard about a similar kind of word in electric charge and electric field topic. In electric charge and electric field topic, you heard about electric field lines or electric lines for forces. And again, by using that, we consider properties or characteristic of electric field lines. Similar to that, today we're going to discuss the concept in a magnetic field that we call it as magnetic field lines. Once you understand these magnetic field lines, we'll do the continuation of this chapter. In that, we're going to think of next important thing. When a magnetic needle or bar magnet, it is placed in a external uniform magnetic field, what should be the torque created, what should be the time period of oscillation, that expressions we're going to learn. Dear student, first we discuss the magnetic field lines. And before understanding this magnetic field lines, dear student, just recall the things what you learn in electric field lines. In electric field lines, or mainly in electric field, we consider two charges, one is plus and the one is minus. And again you consider electric dipole. You already heard about this word, electric dipole. And electric field lines are the one, it is starts from positive charge, ends at negative charge. That concept you learn. And a similar kind concept you're going to think about in a magnetic field line. But here in a magnetic field, we can think about two important poles. I already told these two poles got a suitable strength. And these two poles are called South Pole and North Pole. And again, I clearly said North Pole is equivalent to positive charge and South Pole is equivalent to negative charge. These things I already explained in a previous video. And first we think about magnetic field lines. Dear student, commonly in our annual exam, they're going to ask one question to draw the magnetic field line or diagrammatic representation for a bar magnet. Now this one is a systematic or diagrammatic representation of a bar magnet with the magnetic field lines. You see the diagram clearly. This particular end is called North Pole. North Pole got a suitable magnetic pole strength, I already said. And this particular end is called South Pole. It also got a suitable pole strength. North Pole and South Pole strength are separated by certain distance. We call it as magnetic length. That I already explained. Here, the magnetic field lines are like this. When you're going to see this diagram, one difference you observe when you're going to compare with the electric field lines. Electric field line ಗೆ compare ಮಾಡಿದಾಗ ಈ diagram check ಮಾಡಿದಾಗ ಒಂದು difference ನಿಮಗೆ ಕಾಣುತ್ತೆ. ಏನು difference ಕಾಣುತ್ತೆ ಕೇಳಿದ್ರೆ, in case of electric field line, it never form a closed loop. That we learn. Never form a closed loop, because there are two kind of charge. One is positive and the one is negative. Inside a system we can't think about electric field lines. But here, simple logic, here this end is north, this end is south. From the North Pole, magnetic field lines are coming out. To the South Pole, magnetic field lines are entering. This one is a diagrammatic representation of magnetic field lines in a bar magnet or a solenoid. ಇದನ್ನು ನೆನಪಿಟ್ಕೊಳ್ಳಿ, it is a diagrammatic representation of magnetic field lines in case of bar magnet or solenoid. ಈ ಕ್ವೆಶ್ಚನ್ ಅನ್ನ, ಈ ಡಯಾಗ್ರಾಮ್ ಅನ್ನ ಹೆಚ್ಚಾಗಿ 1 ಮಾರ್ಕ್ಸ್ಗೆ ಕೇಳ್ತಾರೆ. ಇದು one of the important question for exam. Again we discuss the properties one by considering this diagram. First important property or characteristic of magnetic field line. Dear student, this concept also they will ask for either 2 marks or 3 marks. Mention the few properties or characteristic of magnetic field line is also one of the important question for annual exam. We see the properties one by one. ಪ್ರತಿಯೊಂದು ಪ್ರಾಪರ್ಟಿನ ಚೆಕ್ ಮಾಡ್ತಾ ಹೋಗುವ. ಅದರ ಜೊತೆನೆ I will give an explanation with the support of this diagram. First property, magnetic field lines of a magnet form a continuous closed loop. Dear student, remember this word, magnetic field line of a magnet form continuous closed loop. But in electric field you learn reverse. It never form a closed loop. Yes or no? Yes. In case of magnetic field line of a magnet form a continuous closed loop. It form a continuous closed loop. Say this. It will extend further, it will come over here. It will extend further, it will come over here. It form a continuous closed loop. Magnetic field line, it form a continuous closed loop. Is one of the property of magnetic field line. It will form a continuous closed loop. We move on to the second characteristic or property of a magnetic field line. The tangent to the field line at a point represent the direction of net magnetic field at that point. Dear student, first property what I said, the magnetic field lines of a magnet form a continuous closed loop. Once you got the lines like this, for this line at any point, if we take at any point, just imagine if I take point somewhere here. For this point, if I draw the tangent like this, the tangent drawn at this particular point represent the direction of net magnetic field at that point. Dear student, I consider field line, in that field line at a particular any point, yavadu point agatte. For that point, I draw the tangent. The tangent drawn at this particular point represent the direction of net magnetic field at that point. If we take point somewhere here also, for this point, if you have to draw the tangent drawn at this particular point represent the direction of net magnetic field at that point. Now, second important property or characteristic of magnetic field line is the tangent to the field line at any point represent the direction of net magnetic field at that point. Is that clear? Right. Move on to the third point. The larger the number of field lines, crossing per unit area. Larger the number of field lines crossing per unit area, the stronger is the magnitude of the field, or reverse also. Reverse is nothing but the smaller the number of field line or lesser the number of field line crossing per unit area, the weaker is the magnitude of the field. Larger the number of field line crossing per unit area, the stronger is the magnitude of magnetic field. Reverse way, vice versa, reverse way, the smaller the or lesser the number of field lines crossing per unit area, the weaker or weaker is the magnitude of the magnetic field. It should be like this. Just imagine here in case of South Pole, if more number of crowded lines are there, more crowded lines are entering to the South Pole. ಜಾಸ್ತಿ ಲೈನ್ಸ್ ಇದೆ ಈ ಸರ್ಫೇಸ್ ಮೇಲೆ. The same thing, larger the number of field line crossing per unit area, ಈ ಏರಿಯಾದ ಮೇಲೆ ಜಾಸ್ತಿ ಲೈನ್ಸ್ ಬಂದು ಬೀಳ್ತಾ ಇದೆ. Automatically more crowded field line represent the stronger magnetic field. ಇದರ ಸ್ಟ್ರೆಂತ್ ಜಾಸ್ತಿ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಜಾಸ್ತಿ. And more crowded or larger the number of magnetic field line crossing per unit area, more crowded magnetic field line on a given area represent the stronger magnetic field at that particular area or particular point. If it is less number of magnetic field lines, see this. ಇಲ್ಲಿ ಕಡಿಮೆ ಇದೆ, ಇಲ್ಲಿ ಮೋರ್ ಕ್ರೌಡೆಡ್ ಇದೆ, ಇಲ್ಲಿ ಲೆಸ್ ಕ್ರೌಡೆಡ್ ಆರ್ ಮಿನಿಮಮ್ ನಂಬರ್ ಆಫ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಪಾಸಿಂಗ್ ಪರ್ ಯೂನಿಟ್ ಏರಿಯಾ ಇನ್ ಅ ಗಿವನ್ ಸಿಸ್ಟಮ್ represent the weaker magnitude of magnetic field. Magnetic field ಕಡಿಮೆ ಇರುತ್ತೆ. More crowded or large number of field line crossing per unit area ಇದ್ರೆ stronger is the magnetic field. Less number of magnetic field line or less crowded magnetic field line represent the weaker magnetic field at that particular point. Is that clear? Yes is the meaning of third characteristic or property of magnetic field line. Move on to the fourth important characteristic or property of magnetic field line. The magnetic field lines do not intersect. The same kind of property or characteristic you learn in electric field lines also. Electric field lines also never intersect. Similar to that, the magnetic field line do not intersect. Magnetic field lines do not intersect. For if they did, the direction of magnetic field would not be unique at the point of intersection. Keep this point in your mind. The magnetic field line do not intersect is one of the important characteristic or property of magnetic field line. For if they did the direction of magnetic field would not be unique at the point of intersection. ಒಂದು ವೇಳೆ intersect ಆದರೆ ಆ unique property validate ಆಗಲ್ಲ, observe ಆಗಲ್ಲ. That's why fourth important characteristic is the magnetic field line do not intersect. For if they did, the direction of magnetic field would not be unique at the point of intersection. I repeat all the four property once again. Keep this point in your mind. First property, magnetic field line of a magnet form a continuous closed loop. See the diagram. Second important, the tangent to the field line at a point represent the direction of the net magnetic field at that point. See this, I already did the explanation. Third, larger the number of field line crossing per unit area, the stronger is the magnitude of field, or vice versa. That means lesser the number of field line crossing per unit area, the weaker is the magnitude of magnetic field. Fourth important property, the magnetic field lines do not intersect. For if they did, the direction of magnetic field would not be unique at the point of intersection. Along with that, keep this diagram is also in your mind, is an important diagram for exam, mainly for 1 marks. These four properties or characteristic required for how many marks? 3 or 2 marks. Is that clear? Right. Dear student, continuation of this concept. Next important part, the dipole is nothing but bar magnet or magnetic dipole in a uniform magnetic field is nothing but when a bar magnet is also called a magnet or magnetic needle is placed in a uniform magnetic field, automatically that magnetic needle undergo deflection and is mainly depending on the concept called magnetic torque or torque. Dear student, you already learned the expression for torque in a moving charges and magnetism, and depending on that you will learn the important concept called suspended coil galvanometer or moving coil galvanometer. And we consider same equation. Depending on this, we have to find out the expression for time period of oscillation of dipole is nothing but magnetic needle in a uniform magnetic field. Dear student, sometimes they will ask this question like this: obtain an expression for time period of oscillation of magnetic needle or magnet in uniform magnetic field. This question usually they will ask for 3 marks, and this expression is mainly important for a competitive purpose, especially like NEET or JEE Main. Dear student, if I consider one magnetic needle like this one is the one magnetic needle, and I call this particular end is south pole, this particular end is north pole. Dear student, you already heard from south pole to north pole, magnetic dipole moment is acting. Magnetic dipole moment M is acting from south pole to north pole. We already learned clearly magnetic dipole moment M is the product of pole strength of either pole and magnetic length. Remember where M is always directed from south to north pole. I explained in last video. This magnetic needle is kept in external uniform magnetic field like this. Is kept in external uniform magnetic field like this. Is kept in external uniform magnetic field, denote it as B. Here automatically this magnetic needle undergo deflection due to a torque called deflecting torque. Dear student, already around a north pole there will be a magnetic field, around a south pole there will be a magnetic field. If I apply one more magnetic field to that, automatically these two poles experience a force called a magnetic force, and due to that magnetic force, both the magnetic force are equal but they are opposite. It will constitute a couple. We call it as torque. It's called a magnetic torque or magnetic couple. And automatically there will be a deflection like this. This is mainly due to what torque called deflecting torque. I denote it as tau d. Tau d is the deflecting torque with the support of uniform external magnetic field. And due to this deflecting torque, automatically angle swept by this magnetic needle is theta, where theta is called angular displacement, and this angular displacement provide the value for angular velocity. It is leading towards the next concept called angular acceleration. Dear student, where deflecting torque due to external magnetic field, it is tau d is equal to m vector cross b vector, that you already learned. In a vector format we denote like this: deflecting torque is equal to vector product or cross product of magnetic dipole moment and external uniform magnetic field. Here m vector cross b vector. Again, this one we can write it like deflecting torque is equal to mb into sine theta into n cap. I skip the n cap. N cap is a unit vector used to represent the direction. Its value is equal to 1. The magnitude of deflecting torque becomes mb sine theta. mb sine theta. Again, if theta is very small, approximately we can take it like sine theta is approximately equal to theta. Keep this result in your mind. If theta is very small, sine theta is approximately, we can take it like theta you learn. Sine 0 is equal to 0. Sine 1 is very close to 0. Like that, sine theta is very close to theta. If theta is very small, then deflecting torque tau d becomes mb into theta. I call this one as equation number 1. Dear student, when a magnetic needle is kept in an external uniform magnetic field, both north and south pole of the needle, it will experience a force. Both are equal in magnitude but they are opposite. This needle will experience a torque. There will be a rotational effect created by the magnetic force that is leading towards the concept called deflecting torque, with depending on particular angle. Again here, the deflecting torque we can write it like mb sin theta into n cap. N cap, its value is equal to 1. If I take a magnitude, tau d is equal to mb sin theta. I assume the condition that if theta, angle swept by the magnetic needle, is negligibly small or very small, then we can say sin theta is approximately equal to theta. Again, we get the equation tau d is equal to mb. In place of sin theta, I taken theta. I assume it as equation number 1. Dear student, this magnetic needle also got a suitable mass. This magnetic needle tried to oppose the deflection created by the external uniform magnetic field. I repeat, this magnetic needle, it got a suitable mass, it got a suitable inertia. Depending on that, whatever deflection created by this external uniform magnetic field is opposed by the needle by the help of one more torque we call it as restoring torque. Restoring torque is the one, it tries to retain its original condition or original position. And deflecting torque tried to deflect the needle. Restoring torque, what is there in the needle, it tries to restore the condition. Automatically at a particular instant, deflecting torque and restoring torque becomes same, that we call it as equilibrium condition. Automatically, next important thing, restoring torque we denote it as tau r is equal to I alpha. Here I represent the moment of inertia. You heard about that word, you learn under rotational motion and system of particles. Again, alpha is called angular acceleration, where alpha is called angular acceleration. Dear student, same equation you learn in first year itself, a relationship between torque with moment of inertia, torque with angular acceleration, where the restoring torque, it will oppose the deflecting torque, is equal to I into alpha. I into alpha. Dear student, here I assume the formula for alpha is d square theta divided by dt square. D square theta divided by dt square. How we got this formula? Simple logic. Displacement is x. In a rotational motion, displacement is theta. Velocity is v in a linear motion. Velocity v is equal to dx by dt, displacement divided by time. Same way, in a rotational motion, omega is an angular velocity, that is equal to d theta divided by dt, rate of change of angular displacement. And in a linear motion, acceleration is a. It is nothing but d square x divided by dt square. Similar to that, angular acceleration is equal to d square theta divided by dt square. You have to do the differentiation 2 times for displacement, it will provide acceleration. Same thing you learn in case of derivatives under mass. Keep that point in your mind. Displacement is theta, velocity is omega, d theta divided by dt. For d theta divided by dt, do it once again differentiation. D by dt of d theta divided by dt. It becomes d square theta divided by dt square is called angular acceleration. If you do the differentiation 2 times to angular displacement, it will provide angular acceleration. Automatically restoring torque tau r is equal to I into d square theta divided by dt square. I assume that equation number 2. Dear student, there are 2 important torque we got. One is deflecting torque with the support of external uniform magnetic field. That deflecting torque is opposed by the magnetic needle. By using restoring torque, try to regain or retain or restore its original condition. And again I say that as the deflecting torque goes on increases, if I apply more and more magnetic field, uniform magnetic field, automatically restoring torque also goes on increases. At a particular point, a deflecting torque and restoring torque becomes equal. Both are equal but they are opposite. Both are equal but they are opposite. Because deflecting torque acting like this, restoring torque try to oppose. Simple logic, if you take a chalk, I try to bend the chalk in this direction. What is the chalk going to do? Allow or oppose? Oppose in this direction. Chalk I will bend in this direction. Chalk try to regain its original condition in opposite direction. We call it as restoring. That's why at equilibrium, at equilibrium, deflecting torque is equal to minus of restoring torque, because both are equal but they are opposite. From 1 and 2, from 1 and 2, we can say that MB theta, deflecting torque, is equal to minus I into d square theta divided by dt square, where again we got MB theta is equal to minus I d square theta divided by dt square. Equation you got. Further, this equation becomes d square theta divided by dt square is equal to minus mb divided by I minus mb divided by I into theta. I got this equation like this: d square theta divided by dt square is equal to mb divided by I into theta with a negative sign. Dear student, this equation is of the form to represent equation of simple harmonic motion. You already heard about SHM. In a SHM, you learn formula like this: acceleration is equal to minus omega square into theta. Minus omega square into theta. This is equivalent to acceleration. We can write it like d square theta divided by dt square. Here this acceleration we denote it as alpha if it is a angular. If it is a linear, we can take a is equal to minus omega square into y or x. If it is a rotational, alpha is equal to minus omega square into theta. It becomes d square theta divided by dt square alpha is equal to minus omega square into theta. I got this equation. This equation represents the simple harmonic motion. It is a equation used to represent the simple harmonic motion. This magnetic needle start rotating automatically. There will be a formation of SHM. We call it a simple harmonic motion. When you are going to compare these two, idu compare maadi. For considering simple harmonic motion, we get d square theta divided by dt square is equal to d square theta divided by dt square, both are same. Theta is there, minus is there. We get omega square is equal to, what is the answer I got? mb divided by I. Omega square is equal to mb divided by I. On simplification, omega is equal to square root of mb divided by I. This equation I got. But you already know about that. Omega is equal to 2 pi divided by t. Omega is equal to 2 pi divided by t. Substitute here. We got 2 pi divided by t is equal to square root of mb divided by I. Further simplification gives time period t is equal to, taken to this side, 2 pi into square root of I divided by mb is a formula for time period of oscillation of dipole in a magnetic field. Is that clear? Dear student, these are the important step. Just go through this. Simple I did a mash by considering rotational motion concept, deflecting couple, restoring couple, both are equal but they are opposite. Automatically simplify further. This equation is exactly equivalent to this format according to simple harmonic motion, and compare that. We got the formula for time period of oscillation is equal to 2 pi into square root of I by mb. Is that clear? Right. Dear student, remaining thing we'll discuss in next class. Thank you.